Okay. All right, let's go ahead and get started. So a couple of reminders. So don't forget that we have our midterm coming up next week. Ooh, I know everyone's excited about that. So midterm next week. So the midterm will be on Thursday then, and we will review on Tuesday. I still haven't quite decided whether I'm going to make it just completely open note. I'm kind of leaning that way because I haven't rewritten the exam to be more like multiple choice heavy, and so my exams are pretty like free response. So maybe I'll just keep it like such, and we'll be open everything, and we'll see how it goes, and we'll see how long it takes me to grade it. All right, so we'll go with open notes. So that's open everything. Just don't Google. You'll be taking it in here. Yeah.
Does that mean we can use the textbook as a source too?
Yep. So you can use textbooks, notes, anything really. Yeah. Yeah, so you can use electronic notes. Again, I ask, no Googling, no searching around on the internet. And so just another reminder, so I have a lot of people, absent, and it's that time of year where everybody gets sick. And so if you need to make up stuff, so just to keep this on your radar, so I'll just put makeup times. So, right, I teach my Chem 104 Monday and Wednesday from 9 a.m. to 11:50, and it's in the same lab room. I can't remember the exact room. I think it's 312, right, where we're in. But basically, I'm in there, so if you need to make up a lab, you can always squeeze in on this time. Otherwise, you can go to, right, then the Tuesday or Thursday lab as well. Those are just a little tighter, so it can be a tight squeeze, but we can do it. So just keep all those options on your radar for people that need to make up stuff or catch up on labs. Or if you just want to come see me, come find me, ask me questions, you can stalk me there as well. Any other questions before we get going? All right, and I'm watching the chat too, so welcome in the chat. And so we had talked about this last chapter. I got overexcited and forgot that I had it in my lecture notes. But let's at least kind of recap so we can refresh ourselves where we were and kind of where we're going. And so we were discussing this concept of electrons behaving like waves and same thing as photons, right? So we mentioned that light is little packets of photons that behave as both particles and waves. And so this is, again, a recap of what happened with this double slit experiment. And so they said, well, if these electrons behave just like particles, we should just get two spots there, again, like throwing the ball, thinking of classical mechanics. And then like we discussed, that the experiment actually showed this interference pattern. And so that piece of evidence right there was saying, well, actually these electrons do exhibit some sort of wave pattern. And, again, this was kind of interesting at the time, confusing. And obviously, right, the electron, we know it's a small particle. It does have some mass. So small has mass. So all this was pretty interesting to our early scientists. And again, we mentioned, right, a lot of these people were collaborating at the same time, Schrodinger, Dirac. So all of them were able to kind of look at this evidence and have discussions. And so then you get this property here, so the concept of, again, our wave-particle duality, and then also this uncertainty. And so this was also the problem too, right? If you try to study the electrons, you perturb the behavior, right? So you shine a beam of light at your electrons, well, now your photons are interacting with your electrons, so now that makes it difficult to study it because now you perturbed and disturbed its behavior. So that was another issue. And so now, again, we're trying to understand what is going on. And so they said, well, we can characterize an electron as a particle. So, right, we normally say a particle has mass. So we have the mass of the electron. And then a particle, again, now thinking classically, we can describe where it is, right? You can have a ball, you can throw it, you can write an equation for its particle trajectory. So you could find its position. And then energy-wise, we can also characterize it. So we can have, right, a wavelength, a frequency that corresponds it. And again, we get that interference pattern. And so this kind of goes back to, again, the colors of transitions and thinking about those electrons going back down. Again, those energy gaps correspond to a certain color. And so again, the problem is that we can't observe both properties simultaneously. Again, as soon as you try to measure one, now you're interfering with the other one. And so the wave and particle nature are complementary properties. So the more we study the particle nature, the less we know about the wave nature and vice versa. So again, quite a conundrum. And so now we're going to bring it back to Heisenberg's uncertainty principle, and we'll bring up de Broglie again. And so Heisenberg, again, they were trying to measure the electron, so you try to measure its position, and then you perturb it. And so then Heisenberg came up with this uncertainty, and he said that the product of uncertainties in both the position and the speed of a particle was inversely proportional to mass. And so usually you have this. So you can have this written in different forms. So sometimes it's written as uncertainty in position times your uncertainty in your potential, momentum. So this is a symbol for momentum. And so momentum is just defined as your mass times your velocity. And so again, that's uncertainty though, and velocity. So that's this form. So this is a times. So again, you can rewrite this so it's not confusing. And then what are our units of mass in this formula? Kilograms. So put a note to yourself, since again, chemistry is usually in grams, but this is related back to physics. So when we plug this back in, it has to be in kilograms for the mass. Good. And so again, all this is telling us is that the more accurately we know the position, then the less we know the speed. So right, if we try to stop its position to measure it, to gain its position, well now we've messed up the speed entirely. And so let's refresh ourselves as to why this all matters and the difference between our classical and quantum mechanics. So again, our classical physics here, we have a particle and then we can throw it, right? And it has a predictable trajectory. And so let's remind ourselves, so let's do a little recap. And again, figure out why it's relevant when we talk about an electron, but not when we're looking at this. And so let's do a little refresher. And so now calculate the wavelength of a softball with a mass of 100 grams traveling at 35 meters per second. And so before I let you loose, what formula do we need? Because this was from last chapter. What's it asking for? What do we need to calculate? It's not energy.
It's the Balmer formula, I think, is
Mm,
what it's called.
No, not the Balmer formula. There was something else so we calculated that had a wavelength in it.
Would it be the wave particle duality one, where wavelength is equal to h over p?
Yeah, so that one. So wavelength is equal to either h over p, which is momentum, or wavelength is equal to m times v. And h was the Planck's constant. So the de Broglie wavelength formula is what we were looking for. De Broglie. So that's what they mean when they say calculate the wavelength of an object. That's your de Broglie wavelength. What people punch it in. Do people have answers? Looking in the chat too. What do we get?
Is it, 1.78 times 10 to the negative 36?
-36? I think it's a little off. That's like the right ballpark. Did you convert this to kilograms?
Oh,
This,
I forgot, I put 6.26, not 6.6.
so 6.626 times 10 to the negative 34 divided by 0.1 kilogram times this 35.
I got about 1.8 million times 10 to the negative 34.
Yeah, that's what I was looking for, the negative 34. You got negative 34 now too? Excellent. So that sounds right. So 1.9 times 10 to the negative 34 meters. And so I can plug that in. Again, check for calculator errors, especially depending on your calculator and how you have to enter the times 10. And probably want to use parentheses. Yeah, so I get that answer as well there. Excellent. And so again, all that we have verified is this is why in classical mechanics, right, we're not worried about the quantum scale. We don't have to invoke anything different. We just use our classical equations because they work, because the de Broglie wavelength is so tiny, right, that it has no impact, there's no interference, so it doesn't matter. But again, once we get on the scale of the electron, the de Broglie wavelength, like we calculated last time, is relevant.
What does the wavelength do?
Of what?
What does the de Broglie wavelength actually do?
It kind of invokes like uncertainty, and I think it's like the interaction too. Because it just starts like invoking uncertainty basically, because it's like if you yourself are like wave-like, then that makes like that changes your pattern of behavior basically.
So it's to say that it's like oscillating? Does it oscillate like a wave whenever?
Yeah, kind of. But like it's also hard to think about this right in our classical kind of world. Yeah.
And then how do we calculate the number, the de Broglie number?
You mean that?
Well, like, how do we get the 6.626 times 10 to the negative 34?
Oh, this is just Planck's constant.
Sorry, where does Planck's constant come from?
I could look it up, but I mean, it's just a constant right now. So, right, I don't want to go down the rabbit hole of how to derive Planck's constant today. We could talk about that later, but I just want to stay focused. And so this is an idea of how we're going to be treating the molecular orbitals and how we go on from here. So again, classical trajectory, we have just our line outlined by, again, our formula. But now when it comes to figuring out where an electron is, now it becomes an electron density map. So if right, we have the quantum principles applying to our ball here, we would instead say, well, it could be found somewhere along this trajectory. We can't say where exactly. The highest probability density is in the center, and then right, the cloud gets more diffused as we travel outward. And so that brings us to Schrodinger's equation. And again, we're not going to dissect it, right? We're just going to appreciate it, and we're going to appreciate the pretty pictures that come from it. And so all this is saying, so we have, right, our Hamiltonian operator, and it operates on our wave function here to give us some energy times our wave function. And all this, again, we need to take away is that we get solutions to our wave function which are basically, yay, pretty pictures for us. And so if you got bored enough, you could start looking through that atomic spectra PDF that I posted, and that kind of, again, gives you more of the taste of what's going on with the Schrodinger. But again, we're not talking about that in this class. All we're saying is we're going to do a plot of our wave function squared then, and this is where we get our orbital pictures, and that's what gives us, our representations of what's going on, and we can use those pretty pictures to give us actually really good predictions of what's going on then in chemistry and reactivity. All right. And so then basically we'll be looking at the plots of these pictures. And so again, we get this probability density function. And so we'll look at that. Blah, blah, blah. Okay. And so this is just kind of drawn in 3D. So you can see, right, we have X, Y, Z. Again, your little dots are showing where the greatest probability is. So of course, greatest probability of finding an electron in that 1s orbital is towards the center. And then notice, right, it gets more diffuse. So here's the same information just shown as a function of radius. So notice, right, as radius increases out, and you have, right, a node then at this point. So this is showing us our node here, where again, kind of our boundary is. And you can see, right, probability goes towards 0, so you could still have a stray electron right there at some point, but going towards 0 there. And so this is, again, just another plot of this. So radial distribution. So again, where you have the greatest probability of finding your electron. And so your peak maximum here corresponds to then your radius. And then again, you can see how it goes to 0 as you get farther out. And so again, right, this is just telling you where it is most likely found, so at this distance.
So how is that first graph that you showed us in that second graph related?
So they're just different models. So this is 3D, right? And then this is just showing like a 2D approach. So this is just R, so this is either in like the X or Y direction, right? So it's just unidirectional of one side, or it could be Z. But, so that radius corresponds. You're just kind of taking a slice. And then, right, this maximum probability kind of corresponds to wherever, again, your greatest density is. So it's kind of hard to tell from this picture where your greatest electron density is, again, noted by the darker shading. That's what this one is showing. All right, so now we're going to start getting into kind of these quantum numbers and what they all mean. And so your book has a really nice table cheat sheet. So I would reference this as we kind of go back and forth. And so let's see. I'm going to kind of redraw this as well. And so let's just start. Again, we want to start with the 1s. So we could also look at our periodic table. So this should be a recap of electron configuration. But now we're just kind of putting everything back together again. So if we just think about it. So we start at our 1s, right? So we'd label this as 1s. Well, what does that mean? Oops. Now I have too many pages. And so, right, we start with 1s, and so 1 is, right, our principal, oops, quantum number. So going back over here. And so, right, your principal quantum number, this is just telling you, well, what orbitals are even allowed in there. And so in the first one, it's only the 1s is allowed. Again, you can kind of see that from your electron configuration. Okay, we have the 1s. And so other things about our quantum energy levels, so they're just integers. And so basically your Bohr energy levels, so going back to maybe that elementary picture that we've seen, right, are oversimplified. N equals 1, N equals 2, N equals 3. But now, again, we're going into and dissecting what is a part of that. And so that's what we're doing in this chapter. And so again, your values of n have to be any whole number integers, and then they're going to be greater than 1. So we'll look at the other quantum numbers. And of course, right, the larger the n, the more energy and the more orbitals. And so now this brings us to our next quantum number. So our angular momentum number by L. And so all L tells you then is what type of orbital it is. And so if we go back to L, so L has this formula of it can take any values of n minus 1. And they can also be, so negative n minus 1, etc., all the way to n minus 1. And so we'll look at that, what that means. And so all that means for our 1s is that s corresponds to an L of 0. So anytime you see L equals 0, that's just an s orbital. Oh, I screwed this up. This is just values of n minus 1, sorry. N minus 1 for our L. And so they also have nodes. And again, so your lowest energy orbital is the principal energy state. So we'll kind of look at that, excited states. And so again, your s orbitals are spherical shapes. And so the number of nodes is n minus 1. So this one would have no nodes, right? But then once you go to the 2s, well, now there is a node, right, between your 2s shell and your 1s shell. So that's just something to keep in mind. So there's just a small area where there's no electron density. And so this is, again, just an illustration of those nodes. So now if you have the 2s, right, so you just have our 2s orbitals, so like our two little onion rings, so you can see our 1s in the center there, then the node, then our 2s onion ring. And so if we look at this picture, so again, this shows us the same information, just in a different format with this view. So we have our node shown there, again, where it goes to 0. So same thing, this bottom graph gives you total radial probability. So again, this is your max radius, essentially, for your 1s orbital, right? And then this is your 2s there. Questions?
So to find the number of nodes, you just take the principal quantum number and minus 1?
Yeah, for the s, For s orbitals, yeah.
For just S.
Yeah, so this is just s orbitals for their node calculation. And so same thing with the 3s. So again, just appreciating. So 1s, then there's a node, 2s, then there's another node, and then our 3s onion ring. And so again, same information reflected in our other maps from our probability density. Again, you can see where that node brings that probability down to 0. And same thing in this total radial probability. So again, right, this corresponds to our 1s, 2s, and 3s kind of radius there. All right, so let's go back to our periodic table and kind of orient ourselves. So, right, we filled in, so 1s1, 1s2, and we started over here, started looking at our higher nodes, so 2s1, 2s2, and then we said, well, now let's look at the 2p, and so let's go back and again orient ourselves. And so if we start with our 2 now, and this is our principal quantum number, well, now we can have 2 possible values for L, right? So we said L has to equal n minus 1, and so L then can have a value of 1, and it can also take values starting at 0, so we can still have S. So now we're saying at our second energy level, right, we can either have an s orbital or a p. This is s, p. So anytime L equals 1, right, that corresponds to a p. And so while we're doing this, right, I just want to show this at the same time, because again, we're just filling it up in our electron configuration from our lowest energy levels to our highest there. So this is just a good way to orient yourself as well. So again, right, this matches. So we're starting with the 1s, and now, right, we're right here with our n equals 2 for our principal quantum number. And so now let's look at our, back to our L quantum number. So we said L determines our shape, and so we can have values ranging from 0 to n minus 1. And so we looked at our s orbitals. So again, that was L equals 0. Now let's talk about our p orbitals. And so now p orbitals look like little dumbbells. And so now we have our L equals 1 p orbitals. Where are the pictures? There we go. There are some pictures. Although I have just slight criticisms about the shading or something that I want to emphasize, because when we draw them, you want to draw them with opposite shading. So this helps emphasize that the p orbitals have a node inherent to them. And so that's part of the distinction of the p orbitals. And so going back, so we have 3 p orbitals. We'll look at this in just a second. And so again, there's 3 of them. We call them px, py, pz formally. So usually they're in those x, y, z planes. And so again, they're the second lowest energy orbitals. So all this is saying is your s is lower. So we can go back to this diagram. And yes, we always see, right, our s is lowest compared to our p of that same n energy level. And so again, they're all 2-lobed, so they all have that pattern. And again, I would shade them so where they are opposite shading, since that's, again, reflective of how they behave. And so they have 1 node at the nucleus, so they have a total of n nodes. So your 2p, right, has 2 nodes, so one here, and then of course the other one right around it. So between each p, there's also a node. So here's just, again, a radial distribution function. So you can see it drops off to 0, just showing where that node is right at the center there. So again, you can also see, right, it's occupying a different space than our s orbital, since your s orbital is at the center there. All right, let's go back to this m sub l, and let's see if there. And so let's look at formally what it is, and then we'll go through the values. And so this is what I always call, like, which orbital is it? So which exact orbital? And so what I mean by that is, well, we have our big L to tell us whether it's an S, a P, and a D, and an F. Again, we'll get there. But then once you get to that, so right with our S, we have one S. With P's, well, we have 3 P's. D's, we'll learn there are 5 of them. We're getting there. And so our M sub L just tells us which one of these in particular. And so mathematically, they take values of negative L to positive L, including 0. But for S, right, what's our only option for S for our M sub L quantum number? Yep, so it's always 0. And right, so that means our L equals 0, our M sub L is 0 for our S orbitals, so there's only one. And then the other ones, you can kind of see where this value comes from. So it doesn't matter which one's which. I'm just going to call one PX, PY, PZ. But formally, right, this could be 1 then, 0, and negative 1. That's all those numbers mean, is which one it is. So again, a 1 is just saying, oh, it's in PX. And all that's doing is distinguishing those 3, just showing you have 3 distinct p orbitals. So same thing with D. So D, right, we'll learn, well, L has to equal 2 for a D orbital. And so same thing, negative 2, negative 1, 0, 1, and 2 are all your possible M sub L values.
So what is the difference between the 0 in the p orbital and the 0 in the s orbital?
So 0 for the p orbital is, right, the M sub L value. So you'll have your L equals 1 for p, but then any allowed M sub L values are 1, 0, and negative 1. And kind of where this is leading is eventually you can say, like, okay, this electron, you know, has this set of allowed quantum numbers, and that's kind of telling you, you know, where it is located. And then you'll also practice, like, what are allowed quantum numbers. And all that's saying is, right, like an S can't have d orbitals in it, right? Or like your first energy level can't have a d orbital. So that's what we'll mean by allowed and unallowed quantum numbers. And so I'll fill in F, but again, we'll kind of go back to it. But L is 3 for F, and then there's 7 of them. And so again, those will all have values just corresponding to an individual F orbital. People a second. And so again, just kind of rewriting this in a different format. And so now, again, we're at our second principal quantum number. So we have, right, 2s is both allowed and 2p. So now our quantum numbers, and so now we can say, right, allowed quantum numbers. And so usually they write it in this format of N, L, M sub L, and then MS which let's talk about what is MS. So MS, all this is spin, and so do you recall how I always write the little electrons with half arrows? And so that's all that this MS is saying. And you have two possible values, either spin up or spin down, so either plus 1/2, negative 1/2. And it doesn't matter which one you choose when you're writing these. The only thing is, right, two electrons cannot occupy the same position. And well, what do we mean by that? And so let's write then our quantum numbers for helium, or allowed quantum numbers. And so for helium, right, we could write out every possible quantum number that describes our two electrons, since there's only two electrons, so we don't have to go too crazy. And so write electron 1 then. So it can be, and again, following the same format of N, L, M sub L, MS then. So what's our principal energy level? So 1. And then what's the only value of L it can have? 0. Excellent. And then what about our M sub L? Oh, check it again. Yeah, because it's 0 for our S, right? Because there's only one S orbital, so we only have 0. And then this first electron, it doesn't matter if we want to put it up or down. I'm going to put it up formally. But then all that means is for our second electron, when I go ahead and write it now, because I picked this one as positive, yeah, now it has to be negative. And so now this is kind of what I would call, right, our coordinate system for our electrons almost. So now we have two electrons in our ground state, and then we can write out our quantum numbers, right? And this is the same thing as writing 1s2, and then we can write out our s orbital like that. So all saying kind of the same thing. And so now going back to possible quantum numbers for 2s. And so right again for this S1, so now N is 2, since we're on the second main energy level. L is going to be 0, corresponding to our S. M sub L has to be 0, and then MS, right, can either be positive or negative 1/2 there. And so again, treat this as a coordinate system. So if we're on the second energy level, and so now, right, our allowed states, so obviously 2. So of course we have to be at our second energy level to have p orbitals. And then of course we can pick -1, 0, 1. It doesn't matter. And then plus 1/2, -1/2 would all be appropriate quantum numbers. Does that make sense so far?
So this is just like shorthand for like if you don't want to write out every single possibility, like within its own.
Yeah, I'm just
bracket?
kind of showing, because on an exam it's going to be like which one is allowed or which one isn't allowed. So I'm just trying to show, yeah, all the possible. Well, that's good. Usually people don't like.
Well, it shows you where it actually comes from.
As long as people say it makes more sense.
The hard part is that quantum mechanics and this stuff is so like high level, and but we have to understand some of
600 level chemistry, and you don't have all the background information, which makes it hard to understand.
Well, even then, like, inorganic chemists are not going to be solving the Schrodinger equation, or like, you can't do it, right? So that's why this stuff fundamentally is so powerful, because all inorganic chemists do is like start putting these diagrams together. They just get more complicated, and you look at like d orbitals and ligands and crap. But yeah, it's literally putting these silly little pictures together.
Our silly little pictures.
All right, so let's move to our third main energy level. And so again, just kind of reminding ourselves, so that's where we have our 3s, our 3p, and then don't forget our oddness with our 3d starting there. And so again, just kind of recap here. So if we're at our 3 for our principal energy level, and so now possible things that are allowed, oops, not 2s, 3s, 3p, and 3d now is evoked here. And so again, these are just all allowed. And so again, L equals 0 always corresponds back to an S. L equals 1, back to a P. And now we have L equals 2 as our last possible one, again signifying that we have our d orbital. And so let's look at our d orbitals. And so again, we're at L equals 2. So our d orbitals, we looked at all our possible then allowed m sub L values. So again, that's 5 of them, 1, 2, 3, 4, 5, corresponding to our 5 d orbitals. And so then these are where they are located, so dz squared. So let's look at them so we don't just rattle off. But let's kind of appreciate what they look like. So dz squared, and again, I don't like the shading, so I'm going to draw it better. And so now the way this works is the little dumbbell shape is in phase, and then this little donut ring is out of phase, so that's the appropriate shading there. And so again, z squared, so that's going up and down in the principal rotation axis. And then all the other 5d orbitals are located in just the plane. And so let's do this one last. So notice yz, xy, and xz are between all the nodes there in the plane. So you can kind of see that. So notice, right, your xy one lies, and let me kind of draw this, in a top down. So you have xy, and then your lobes are in between there. And then the shading is like this, so kind of same across, but then these are opposite, so these are kind of out of phase, but in phase for other things, but we'll save that for later in the course.
Do the phases, can they like switch over?
Yeah, so I just drew them as like dark and light, but you could draw it as light and dark. But yeah, they can't just like switch all the time, but like the colors is also just a formality too. But it'll make more sense once we actually do more MO diagrams, which unfortunately we don't do till second semester. So we're gonna get like a taste of this and then put it away and then come back to it later. And then so again, same thing, this is between the planes. So right, notice your Z plane is there, so you have your nodes there. So YZ, it's in again our YZ plane. And you might want to draw the shading to remind you. And so same thing, right? XZ is in our XZ plane between them. So I'm just drawing the shading or filling in. And then this last one, x squared minus y squared, you can remember it's funny because it lies on the actual axis now. And so I'll draw that from a top-down view just so we can compare. So again, x squared minus y squared actually lies on the xy axis. And I apologize, I can't draw symmetrical lobes, but you can at least appreciate the shading there.
So the shadings are representing different nodes, right? Where it's not shaded, there's nodes.
Yeah. Yeah, well, so anywhere, so to get into, so there's a couple things we see. So again, going back to right, like this 1s, there's no nodes because there's no shading. But then the p, yeah, you have one node from the opposite shading. And then the d, yeah, so now you have two nodes, so that's why you have the technically alternate shading. I really cannot draw symmetrical lobes. And so going back to our D overview, so again, yeah, they're all this 4-lobe shape for the most part, and then you saw the DZ squared with the, I always call it the donut ring. Questions? And then, of course, right, we can go through all the allowed values. So I just want to emphasize, so again, our M sub S has to be 0 for our 3S, right, our 3P. M sub L has to be -1, 0, or 1. And then, of course, D, all the allowed M sub L values. Oops, I skipped 0. So is that making sense to people? And so again, right, I'm just kind of rewriting this chart just in a different way. So it's just all the same information in this chart as well. And so let's go back to electron configuration. And again, this shows us kind of why we go, so 3p, 4s, 3d. And again, all these are very close in energy level. We've kind of touched on that. That's why we had, again, weird electron configurations in the D block. And so just kind of recap, so 3p, and then we started 4, right, so 4s, back to 3d, then 4p, 5s, blah, 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 4d, 5p, 6s, and then here, right, with our 4th energy level, now we should be able to invoke our next orbitals, so our 4f. So again, just a recap, and I probably should have put, just for clarity, for us, oh my gosh, 4f here, and 5f, which is actually what's reflected in these electron configurations, but I just want to make it really clear. All right, so now let's look at our last, at least relevant one. And so again, right, 4 now is our principal quantum number. And so now everything that is allowed is, right, 3s. Why do I keep doing that? 4s, 4p, 4d, and 4f. And so again, right, we have our L's. So this is starting to get fairly repetitive. So now L equals 3 goes for our F orbitals. And so let's look at the pretty pictures. And so, of course, we'll have our M sub L of -3, 2, 3. There are 7 of them. 1, 2, 3, 4, 5, 6, 7. So corresponding to all 7 F orbitals. And I have never drawn them out personally, and so they all look crazy. I am admittedly not even familiar with their names, so you can appreciate them. They exist, so they're pretty weird. So I would just appreciate them, look at them.
So each orbital kind of rests within another orbital's node, right?
Kind of. I mean, it gets like fuzzy in there. It's pretty packed and crowded, and we can do some computational chemistry later too that kind of gives us a picture, but it's all just our best kind of understanding of what's going on as well. And
Do we need to know the subscripts and the different orbitals in these?
all these thingies,
Yeah.
no, just know that there are 7. Like I said, I don't know them,
Yeah.
and yeah, unless you started doing like lanthanum or actinide research, you probably don't talk about them. Or,
I need to know them for the previous ones I
I wasn't planning on like explicitly quizzing you on this, but I would at least be familiar like for your going forward knowledge, because the D's come up forever and ever. Like usually that's something that people talk about, and like modeling D orbitals and like looking at them and blah blah blah. Same thing with like, you know, the P's. Obviously you want to be familiar that they're dumbbell shaped, but yeah, not normally do we ever talk about the F's. All right, so going back to our F's, so again, write all our possible numbers. So just kind of writing them out so people can see. Again, it's getting a little repetitive, but write all our possible combinations. And so of course you could continue this out to, in theory, like there's theoretical orbitals of G, right? So then that would have 9 orbitals in it. So it just keeps following that same pattern, but since we haven't discovered any elements that need to invoke that, we're not going to continue for all craziness.
What would be like the atomic number of something that has to be? You don't have to answer that.
big number.
Big.
I'm trying to think, but I'll get back to you on that. Other questions?
So can we go over the node numbers for each of the orbitals, like of the shells? So like the nodes for the s orbital would be 0, or would it be 1?
So the S is n minus 1. So the 1s has no nodes, but then the 2s has 1 node. So it always has like 1 less node. And then, so just last things on this page is just be familiar with, again, other ways to represent kind of the same information. So you can see, right, this is just kind of drawing your orbitals in a different way. So kind of a side view, and each little box is an orbital, so you could fill that in with electrons. So they don't have them filled, but you could draw in little electrons, or sometimes, right, you see them with other some sort of box notations. You could fill those in. And so then other kind of hints and cheats. And so in general, the following are true. So the number of sublevels within a level are going to be equal to n. Yeah.
When it says sublevels, is that the same term as subshells?
Yeah, so like
Doesn't
S,
follow the
P,
next
D, F.
Yeah.
Yeah. And then the number of orbitals within your sublevel is 2L plus 1. So that's just corresponding. So of course, right, with S, that's just saying there's 1. Right, 1S, 3P. So you could plug in, right, P is 1. So 2 times 1 plus 1 is 3. So that's all that's saying. And again, you can continue the pattern. So D, 2 times 2 plus 1 is 5, etc. And then number of orbitals in an energy level can be simplified as this. So n squared. So again, for S, that works. So n squared is just 1, right? There's just one S. And then you can't go on, right? 2 squared. And then if you want sometimes they ask for number of electrons. And so that's just 2n squared, right? So whatever your n squared is times 2 just gives you your electrons. And then this number, the number of electrons corresponds to what I always say is like your elementary school level, right? So n equals 1 gives you 2 electrons, then 2. So 2 squared is 4, which corresponds to your s and your p orbitals, which is 8 electrons. And n equals 3, that's where you get 18. And n equals 4, right? 4 squared, 16, 32. And n equals 5 just for kicks, so 50 electrons there. Right. Other questions so far? So let's do a practice then. So this is just electron configuration recap. So is everybody okay on electron configuration? You can always go over it. So blah, blah, blah. So this is just all the same thing. So this is just reminding us how to fill it in. Again, right, putting 1 electron in each degenerate orbital. All right, so let's do some practice. And so first, write the electron configuration. And let's do barium. And also give an allowed set of quantum numbers for the valence electron. see, do we have answers? Does someone want to put it on the board? Watching the chat as well. Yeah, go for it, Andrew.
So first it is take the electron configuration. Starting with xenon, 6s2 left over corrected. And the quantum numbers, first one is 6, because of this 6 here, and then it's an s orbital to the L0, and so is the m of L. And last one is the same with plus or minus 1/2 for this one. So look right?
Yeah, that looks excellent. Is that what everybody else got? So excellent. I see a lot of nods. So probably the tricky part of that was since I asked specifically for a valence electron, you wanted to put 6 for your quantum number there, just signifying that we're on the 6s, but and then everything else looked good. So of course, right, don't get tricked and put anything crazy here. And so now let's do another practice. So now let's take this barium, and now can we write a possible electron configuration for an excited state of barium? What is that? How is that different?
Would we be invoking p orbits?
Yeah, you could evoke anything. Sky's the limit here. Someone want to put it on the board?
May I give it a shot?
Yeah, go for it.
I have no idea if this is right. But maybe. That's on me,
Yeah. So this one, right, we can go nuts. So this is totally allowable, at least from our information. So yeah, leave one there and then only promote one. So that looks good. Did people come up with other variations? Other
Could you-
answers? Yeah.
Could you have also done like 6s0, 6p2?
My only issue with that is usually we just want to like promote one electron
yeah.
at a time. That being said, on your homework and stuff, you might see examples like that. So that's, yeah, that's totally like an excited state. So that would be okay.
Favorable?
Yeah, well, just from what I've been reading kind of about the research, is like usually one stays in the ground state, and then you're just watching that transition of just a single electron.
So then would it be possible to like go back instead of having xenon as your like noble gas base, have krypton, and then all of the electrons after krypton are possibly excited to a higher state?
That's just a lot of core electrons, though.
Okay.
That's my, yeah, only criticism. Is that it's probably going to come from the valence one. But there's still other possible combinations.
So you could just go one past and do 6s1, 6d1.
Yeah, so 6s1, and then not 60 though.
Would be 5D.
Yeah, 5d1 would work. You could take it up to an F. Right, xenon, 6s1, 4f1. You know, why not? We don't really know. So these are all other possible solutions. I mean, you could get really crazy, right? I mean, xenon, 6s1, 7s1. Like, nice, yeah. Yeah, I mean, why not? We don't have enough information to know whether it's allowed or not, so yeah. As long as it's the right, if you have the right excitation, yeah, it could go there. Yeah, all these are allowed, so all you're looking for is like, is it higher? Oh, this one only goes so far. We could always pull up our P table to kind of help inspire us as well. Like, oh, what are all our options? All right, let's try some more.
So then would an excited state change the like coordinates that we were writing out earlier?
Yeah,
With n equals whatever, L equals something.
yeah, so then let's do it for this one. So now write some allowed quantum numbers. And then, Tori, I saw your hand up. Okay. Does someone want to put some numbers on the board? And so there could be multiple solutions too.
I can try.
Yeah.
I don't think I have a very like strong handle on it.
See what you got.
For the coordinates, I believe it would be then plus or minus 1/2. Does that make sense to anyone?
So my only issue, so where's the F orbital though in this one?
That would be under the L because L equals 3 in the F orbital.
But then what's its principal number here though?
So then this 6 would become a 4
Yeah.
instead.
Yeah, because it's really in the 4. So if we're doing it for this 4F1, then it needs to go in the 4. And then, yeah, then 3 is fine for F. And then we can pick any of those values for M sub L. And then, yeah, 1/2 or negative 1/2. So that works better. Just so we know that this F orbital is really still in the 4N energy level.
So when you're doing these coordinates, you basically you have to use the like biggest orbital.
Yeah, that it's in. Yeah, because otherwise, when you say, 6, 3, negative 3, negative 1/2 or whatever, this is kind of saying we're a 6F orbital. Yeah, which is theoretically allowed, right? There's nothing wrong with having an F orbital in the 6 energy level. I never answered Vaughn's question, but right, basically we don't need to invoke 6F, right?
Okay.
So there's nothing that exists out there.
So the allowed quantum numbers for the 6S1 would still be the same?
Yeah, so then, yeah, this one is still the same. So if we wanted to write it for this, right, it's our 6 and then our 0, 0, positive negative 1/2, which would still be, which of course, right, is another possible combination for these electrons. So let's do some more practice. And so let's see. So assuming this is for a ground state atom, what element, and it could be several elements, could this be? And say this is for our valence electrons. And so let's say our quantum numbers are 3, 1, negative 1, negative 1/2. So what elements could it potentially correspond to? Do we have guesses? Let's hear some. So I hear phosphorus. What else do we get? What is this saying? First of all, so what is this telling us?
It's telling us that it needs to be in the 3p, well, the valence is the 3p orbital, basically, that's the most outer shell.
So excellent. So we established it's a P. So I heard phosphorus. What else do we get?
I said anything from aluminum to argon, yeah.
So we took the everything approach. I like that once I find my periodic table. So y'all told me it was 3P. So yeah, if we want to be super inclusive, everything from aluminum to argon is a perfect answer there. So you could have picked any of those. Excellent. Oops. Now I lost my aluminum to argon. Excellent. All right, let's play that game again since you guys are so fast at it. So which valence electrons so what do we have this one? You have an answer already? Let's see, is everybody ready? All right, go for it. What's your answer? What is this saying, first of all?
It's saying that it is N5 in the D orbital, which means it would be everything from hafnium to mercury.
That sounds good. We could put in actinium too, right? Don't forget about that. Because that, or not actinium, lanthanum, sorry. Misread.
Right, yeah.
Yep, lanthanum too. Mercury sounds pretty good. Is that what other people got? So again, main thing, as long as you're identifying, right, N equals 5, D orbitals, so then that kind of orients
Question,
yourself.
that would only include lanthanum, right? Not like cerium.
Right, not,
Cerium and 4F.
yeah, exactly. So not them.
Yeah, number 57 and then
Yeah.
72 through 88.
Yeah.
Okay, thank you.
And that's about as precise as you can get with these coordinates, right?
Yeah.
You can't like narrow it down to a specific element.
Yeah, because we don't know like what d orbital entirely we're talking about, right? We're just giving them formal assignments, but there's no like cross, reference. All right, let's see what else is in this chapter. Y'all have kind of destroyed this chapter. Well, it's also because we did electron configuration earlier, which kind of helps. So are we feeling okay on electron configuration? Okay, so we all feel okay about this. So it's there for your reference. We continue it. Let's see what else is in this chapter. And so we're kind of already over here. And so this is just practicing writing electron configurations for excited states. And so this is just lithium, of course. And so we can write our electron configuration for lithium, of course, ground state. 1s2, 2s1, And then they just showed us pictorially. Again, we're just looking at the outermost electron. And so now, of course, excited state, which you all have caught on pretty quickly with this. So 1s2, 2p1, or, right, again, not limited to this. You could go crazy, taking it to the 3s or whatever. So you could write a ton of potential combinations. All right.
Question
Oh.
about the tests in this chapter. Will you want us to memorize the specific like names of the principles, like the Pauli exclusion one for like 2 electrons of the same spin can't be in the same orbital?
No,
Just the ideas?
yeah, all you care about is they fill up, right, lowest energy level first. They don't want to pair unless they have to. And then, right, that's why you fill up each one and the degenerate ones. Yeah. So I think y'all are good at this, but let's do it again. So let's do some more. So write your possible electron configurations for excited states of hydrogen. So let's start hearing, what do we get? 5F1. I like it. So of course, I'll just remind everybody, right, what a ground state is. Other
I put 2p1.
2p1. 7s1. Yeah, it's like those excited states. Yeah. Any other ones? 2s1. All right, I like it. So that's pretty good.
And if you're gonna write this out, like for the 2s1, you would do 1s0, 2s1 if you're writing it out.
Oh yeah, you could write it like that, but yeah, oftentimes you just don't even write it if you're writing like the skipping to the excited state. All right, let's try to finish up this chapter, and we'll kind of see how much practice we do on Thursday. And so now we should look at our atomic radii trends. And so let's just look. So this is starting going from lithium all the way across to fluorine. So starting here, right, going across to fluorine or neon. Oh, they didn't even put neon, that's weird. Then back, right, sodium, going down to chlorine. So let's first talk about, well, let's look at the trends with each of these alkali metals. So lithium, sodium, potassium, rubidium. So what do we notice about the radius?
All the alkali metals have much bigger of a radius.
So we can say the alkali metals have the biggest radius. And then what's the trend you notice as we go down the periodic table?
The more electrons you add, the like tighter they are.
Oh, that's across. What about just, so now,
Oh, no, okay.
let's start simple first. You're not wrong, but,
There's a big jump between the first, like, the metal and the next.
oh, like lithium to, well, so I was just comparing like lithium to sodium though, like to potassium. Or as we go down, right? So all I was trying to show, so right, lithium, sodium, potassium, rubidium, cesium. So we're starting with the easy trend. So right, as you go down the periodic table, so of course we add more shells, so we have an increasing radius. Right, so increasing down the periodic table. And so then a lot of people were already catching on that, well, as we go across, it gets smaller. And so why is that? I think,
I would assume it's because they have more protons, which makes them want to like hold on to their electrons more.
so kind of, but, so let's compare fluorine versus boron for a second. And so what's the electron configuration of boron, or how many valence electrons?
The 3 valence electrons.
So 3 valence electrons. And so, right, we'll fill this in. So 2s2, 2p1. So filling them. So it only has 1 in the p. And so what's fluorine's electron configuration?
Be 2s2, 2p5.
Excellent. So, right, we have 7 valence electrons versus the 3 here. So we'll fill them in and drawing them in appropriately. And so you kind of have the right idea, but let's just nail this down a little bit tighter. So, of course, these are both neutrals. So right now we're just talking about neutrals. And so with both of these, right, protons and electrons are the same, except with our fluorine here. So if we're filling in more electrons on that 2p, it means we're putting them in, right, the same radius, so the same distance apart. So as you fill in more electrons, this essentially has a greater effective nuclear charge, and it's able to bring it in tighter, again, since you're adding those electrons to that same energy level, so the same radius away, same distance away, and then it brings them in tighter, so giving you the contracting radius there. So versus boron, again, filling in, and so it doesn't have as many filled in that P, so it's unable to bring it in as tighter. And so you can see that right with lithium, and so everybody noticed how those, there was quite a gap there. And so that must be significant, so going just from lithium then to beryllium, so just kind of comparing. So you're only looking at the 2s with both of these. But again, you can just imagine the significance that makes of just having 1 in that 2s, again, very loosely bound, so kind of fluffy radius, versus, well, now that we have 2 in the s orbital, that must help it contract a little. And so you can even note, right, not much of a radius difference between beryllium to boron, and then, of course, continue to contract there. So then that general trend.
What I don't really understand is the more electrons you have, like wouldn't the electrons themselves be repelling each other and wanting to be farther apart from each other, which would increase the radius?
But they're still going in like separate orbitals though too, so that kind of helps. But it's also, you still have to think about it, right? You have, in this case, like 5 electrons in that 2p radius, so set in those 3p orbitals so far distance apart. But that still means that the effective charge is stronger, right? Because it's still able to bring those electrons in. Like even just compared like nitrogen, where if it only has one electron in those P's, you know, it still brings it in, just not as tightly as you continue to fill them in, right? And have more of that effective charge.
Oh, so does that have to do with the plus or minus half a charge in the, like, coordinate thing that we were doing?
Kind of, but it's more like effective nuclear charge, except for our purposes, we're not really calculating it because truly, like, yeah, you have to count all the repulsions, but yeah, we're just kind of like oversimplifying. So kind of the idea is, let's say, right, you have a sodium versus a chloride ion versus a magnesium and a sulfur. And basically, these two have a stronger effective charge because they have higher charges, so they're more like attracted. And so kind of the same principle we're invoking, but not quite the same because these aren't just like static point charges. They're, like you mentioned, you know, there's multiple complex interaction with them being paired, but again, just kind of overall simplifying it. All right, so that gives us, again, decreasing radius as we go across. So of course, funky trends in the transition elements. And so let's also look at, so what happens if we have a cation radius? How do they compare? So let's just take, right, regular potassium versus, so who has a smaller radius?
I would assume the cation?
Yeah, so the cation does, right? And so just like you were kind of thinking, so back to this potassium, so of course that valence one is most loosely bound, and let's look at our other periodic table. So right, potassium has our 4s1 valence electron, and so of course that gives it a diffuse radius, 4s1, and then of course it's ejected, and so that brings us back to argon for its electron configuration. And so yes, it would always have a smaller radius. And so right, positive charge, that means also can bring in those electrons tighter now, the nucleus. And so you want to say for cations, so cations, right, are always smaller than the neutral. And so now let's compare that to anion radius then. And so just for kind of thought, we could do sulfur versus sulfur 2 minus. So what do we think? So sulfur is going to have the smaller one by itself. So exactly, right? Yeah, so exactly. So right now we have electrons, and we could write our electron configuration. So 3s2, 3p4 versus 3s2, 3p6. And of course, right now we have too many electrons. So now the nucleus cannot hold on as tightly. So this would be larger. And so, right, you want to say with anions then, so the neutral is always smaller, right, compared to the anion.
And it can't hold on tightly to all of the electrons in the 3p orbital, right? Not just the 2 extra electrons that it...
Well, yeah, it's all of it makes it have a diffuse orbital then. So now because it has that negative charge, yeah, it's unable to hold it in as tightly. So even though it has that filled radius, right, it's because of the mismatch now. So now you have too few protons, so now they're nice and fat. Okay, let's see. Let's do some more practice without doing this practice. I guess we can do this practice. All right, let's try. Let's see how far we get. Try with this first one. So what is the uncertainty and velocity of an electron whose speed is known to within 2 times 10 to the negative 8 meters? So if the electron is moving at 5 times 10 to the 5th meters per second, what fraction of this speed does the uncertainty represent? How's your problem? Also, I probably should have given you the mass of an electron at least.
Yeah, I
But,
don't remember the mass of an electron. I don't think I wrote it down in my notes either.
all right, I wrote that on there. And I think you should be able to solve it. Give people like another minute or so. Does anyone want to put it on the board of what they started?
Yeah, go ahead.
Let's see.
So my setup for this, I'm just gonna, for clarity's sake, rewrite equation. So it's your uncertainty in x times your uncertainty in the velocity. That's constant over 4 times. So this is going to be 2 times 10 to the 4th v.
So that looks pretty good. I have no complaints. So now you just have to do the math and plug it in.
And this is how far I got in my paper.
So what do we get for our uncertainty then? Velocity. Watching the chat too for answers. I hear calculators punching away.
Are we only at 166?
Yeah, from this, you could give it 2, just so it's not super awkward. Technically, I should have put like 2.0 or something to help us. Yeah, that looks good.
Okay, good.
Yeah. So that's what I got. So about like 3,000 roughly. Is that what
Mhm,
everybody
yeah.
got? So excellent. So that's an uncertainty of about 3,000.
You mean 30,000?
Should just be 3,000.
Oh, yeah. Right.
So
Just like
about 3,000 meters per second. And then the last little bit was what fraction of the speed does it represent? So it's moving at 5.5. So now we just need to divide. So 3,000 divided by 5 times 10 to the fifth to get a percentage. And of course, times it by 100 to get it to a percent. Oops, sorry. And so times 100. So about 0.6% roughly uncertainty, so not terrible. So 0.6% uncertainty. And so if you're thinking of error, right, so then this is kind of your error, plus or minus, since we can only get to within this amount of certainty. All right, I think we are out of time or over time. So we'll continue on Thursday with more practice, so bring more questions. We'll keep practicing. And then I will see half of you in lab. And then I'll hang out another minute or so online on the stream in case there are any questions. Thank you too for being here.
just a general ASG.
Maybe we all have to do it, so.